Welcome to Management 670. Today we will continue on discussing descriptive statistics, and this time discuss skewness and shape of distributions. Let's get started. We've covered central tendency before, along with the variation, and now we're to the last part about the shape, how the distribution actually looks when graphed as a histogram. First, I want to discuss skewness. Skewness can be a description, or is a description, of a distribution and how it appears, how it's dispersed. We say that a data set or data can be symmetric or skewed. It's symmetric if the mean and the median are exactly the same, and it has tails both to the left and right. We say something is right-skewed or positively skewed sometimes when a few large values pull the mean away from the median, making the median less than the mean itself. So it also often has a small tail to the right. A left-skewed distribution, or negatively skewed, is the opposite. It's when you have a few very small numbers that pulls the mean away from the median. Therefore, the mean is going to be less than the median. In both cases, extreme values pull the mean away from the median. As we can see here in this graph, symmetric is nice and balanced. It shows the mean and the median are the same, while the left-skewed and the right-skewed have a non-symmetric distribution. For the left-skewed, you have a tail that goes off to the left. Those few small values are influential, pull the mean away, but of course don't do anything to the median. For the right-skewed, on the other hand, you have a few large values, so the mean would be to the right of the red median line right there. Below our graphs are the box plots, which I'll get into a little bit later, that show these relationships. To put a numeric value on skewness, we will use the coefficient of skewness, often shortened to CS, and it's to measure the degree of asymmetry of observations around the mean itself. You take each observation, subtract mu, the overall population mean, and take it to the third power, cube it. You then divide by the cube of the standard deviation, and that once you're all done, you divide by the sample size n. Below, at the bottom of the slide, we see several rules. If a coefficient of skewness is non-zero, then we say it has some degree of skewness. For instance, if it's greater than 0, then it is right-skewed. And for any CS value over 1, we say it's highly right-skewed. The reverse is true for negative values. Any distribution that's left-skewed will have a CS of something of a value that is negative, and any CS value that's less than -1, we say is highly left-sensitive or left-skewed. The closer the CS value itself gets to 0, then the less skewness it actually has. For the empirical rule for bell-shaped distributions, we have a very handy fact sheet below. The normal distribution is symmetric, as the graph below shows. Within one standard deviation, either positive or negative, we say approximately 68% of values can be found there. But that number jumps to 95% within 2 standard deviations. And then finally, 99.7% within 3 standard deviations. Kurtosis is actually a description of the thickness of the tails of the distribution itself and how it compares to that normal distribution on the previous slide. Kurtosis is used to evaluate risk because the larger the value of kurtosis for a distribution shows the more potential for extreme or catastrophic outcomes. Similar to the coefficient of skewness, we have a coefficient of kurtosis. In this case, it's CK, and its equation is found right here. It's very similar to the correlation of skewness, except to the 4th power instead of 3. As I said, the higher the kurtosis number, it means the more area for the histogram of the distribution in which the tails are larger than in the middle. 3 is the cutoff point. Any CK value less than that is often described as flat or not peaked. And any CK value over 3 is often referred to as peaked or fat. This means it has less dispersion. Let's take a look at an actual problem. So below I have 80 different values of selling prices for homes in a college town real estate agent gathered this data set, and I'm interested in the skewness and the kurtosis of this distribution. We could put this data into Minitab and automatically generate the summary of the distribution. So I have a mean of about 129, standard deviation of just over, or pretty close to 12.3. But then right below the variance right here is the skewness level, shows it's positive, and a kurtosis level that is over 3. And sure enough, when we see the histogram itself and the underlying normal distribution, we see that we have a few extreme large values here that's pulling the mean away from this median setup right here. I now want to talk about z-scores. They're a measure of a relative location of each observation, and they are often called standardized values. A z-score denotes the number of standard deviations away from the mean that an observation is. So you subtract the observation value by the mean, the population mean, and divide by the population standard deviation. Therefore, any mean value, any value that has the mean value, is a z-score of 0. A z-score of less than 0 represents that it's below the average or the mean, and a z-score greater than 0 represents that it's greater than. The z-score is the distance away measured in units of standard deviations. Going back to the real estate example for the housing data we have, the mean is about 129. Standard deviation is 12.27. So if I took all 80 of those values, subtracted the mean, and then divided by that standard deviation, I would create the following table of z-scores for all 80. They range from negative 2.2 standard deviations away all the way up to 4.66. We don't have any observation that was exactly the mean, which is fairly common, but we have some that are very, very close right here. This brings me to a discussion of an outlier. An outlier is an unusually small or an unusually large value in a data set. Usually, an outlier is thought of as a z-score that is less than negative 3 or greater than 0.3. And going forward in our class, that's what we will consider as an outlier. I want to warn that you cannot automatically throw out an outlier and just assume that it is a mistake. It might actually be correctly recorded and fundamentally a part of the distribution itself. Going back to the results from the Minitab example of the housing prices is the box plot. For a box plot, we say that we have several features here. We have the vertical line, that's the median in the box. Q1 is the first vertical line of the box, and the rightmost vertical line is Q3. So by definition, we have half of the values found in the box itself. Notice that the mean is a little less than the median right here. We have IQR, is the interquartile range. And I want to define an outlier as any value that is outside 1.5 IQRs, or interquartile range values, away from the box. We say these horizontal lines coming out of the box are whiskers. And Minitab automatically will star any value it believes to be an outlier outside of this range. That is, any value that falls outside of the range of these dotted red fences right here. Overall to the right, I have a calculation of where those fences are located. So we can see that any value that is less than about 94,000 or greater than about 163,000 should be considered an outlier for this data set. I'll go back to the previous slide and see that we have one observation right here that is more than 4.5 standard deviations away. And sure enough, going back to the box plot, Minitab has marked it as an outlier and circled it with a star. Finally, in addition to the empirical rule, we have a more general description of how distributions behave. It's called Chebyshev's theorem, and it says that for any data set, any underlying distribution, we can calculate roughly how many of those observations will be within a certain number of given standard deviations, in this case denoted as k. So for example, any distribution at all will have 75% of all observations within 2 standard deviations away. That jumps to 89% for 3 standard deviations away, and then 94 for 4 standard deviations away. Note that this is very different from the empirical rule, but for the empirical rule, we know what that underlying distribution is. For Chebyshev, this is general and works for any data set and any distribution. So in conclusion, descriptive stats give a variety of values that describe a large set of data. In this section, we discussed the shape and the skewness and how that relates to the values themselves. Thank you very much.